On the short grass plains of the Masai Mara, a zebra carcass has been dead for 11 hours, and the air around it has already turned into something close to a biological weapon. A white-backed vulture drops out of a thermal 1,000 meters up, wings angled back, and lands hard, 30 meters from the carcass, in a spot already crowded with a dozen others of its kind, jostling and hissing over territory before the feeding has even properly begun. It walks the rest of the way on foot, bald head lowered, and when it reaches the carcass, it does not hesitate at the torn opening in the animal's abdomen. It plunges its entire head and most of its neck directly into the body cavity, into tissue that has spent nearly half a day fermenting in equatorial heat, swarming with bacteria that would put a human in intensive care from a single open wound. Watch it closely, and something becomes obvious almost immediately. This bird is not being careful. It is not picking around the worst of the raw the way a more cautious scavenger might. It is eating the organs first. The liver and the intestines, the tissue, already dense, with the specific bacterial colonies that thrive fastest in a dead body's core, and it is doing this with its bare, exposed, unfeathered skin in direct contact with fluids carrying strains of Clostridium, Salmonella, and Escherichia that have already been documented in laboratory culture, at concentrations high enough to kill almost any other vertebrate on the plain. It will do this again tomorrow, and the day after, on a different carcass, feeding this way for the rest of a life that can stretch past 30 years in the wild. It should not be possible. Every basic rule of vertebrate physiology says an animal that repeatedly submerges its head in bacterial loads, this dense, should be sick constantly, dying young from exactly the kind of gut infections and systemic toxin exposure that make raw carrion one of the most dangerous substances a mammal can put in its body. And yet across the full range of both Old World and New World vultures, from the white-backed vulture picking apart this zebra in Kenya to the turkey vultures gliding over roadkill in rural Texas, documented cases of a vulture actually falling ill from the bacteria in its food are, by comparison to any other scavenging animal, remarkably rare. Something inside this bird is doing an extraordinary amount of invisible, continuous work, and the first and most immediate part of the answer sits not in its immune system at all, but in its stomach. Vultures belong to an ecological category researchers call obligate scavengers, meaning carrion is not simply a fallback food source, the way it is for an opportunistic hunter like a hyena or a jackal. It is, for most vulture species, close to the entire diet, and that specialization stretches back tens of millions of years, long enough for evolution to have had ample time to solve the disease transmission problem that comes bundled with it. A 1975 study, led by David Houston and John Cooper, examining the digestive tract of the white-backed vulture directly, measured something that reframed how researchers understood vulture physiology from that point forward. The stomach acid inside a vulture's gut registers at a pH close to 0, among the most corrosive digestive environments recorded in any living vertebrate, powerful enough to dissolve bone fragments, and, critically, powerful enough to destroy the great majority of bacterial pathogens on contact, including organisms that survive essentially anything a human or a domestic dog's digestive system could throw at them. That corrosive stomach is not incidental to how a vulture eats. It is the load-bearing wall the entire lifestyle depends on, and it explains why this particular scavenger can plunge headfirst into rotting tissue that would put almost any other animal into septic shock within days. But acid alone did not fully answer the question, and researchers pursuing it further found that the story was not as simple as a single powerful stomach, neutralizing everything that entered it. Because before any bacteria from a carcass reaches that stomach at all, it has to pass through the vulture's mouth, throat, and facial skin, territory the bird's bald head sits directly inside of every time it feeds, and territory a 2014 study led by Michael Roggenbuck and a team examining the gut and facial microbiomes of black vultures and turkey vultures across the southeastern United States found to be almost unbelievably contaminated. Swabs taken from the facial skin of wild vultures, sequenced and cataloged in detail, revealed a dense, diverse bacterial community dominated by exactly the kind of pathogens carrion is famous for carrying. Genera capable of producing potent toxins and triggering severe illness in most other animals exposed to them at similar concentrations. That should have been the end of the story in the wrong direction. A face this contaminated should produce a gut equally contaminated, feeding a bloodstream saturated with dangerous bacteria on a near daily basis. Instead, when Roggenbuck's team sequenced samples taken from deeper in the digestive tract, past the stomach, the bacterial diversity collapsed. Species after species that had been abundant on the facial skin simply were not present, or were present only in drastically reduced numbers, in the lower gut. Something was filtering the vast majority of that dense, dangerous bacterial population out of the system entirely, and only a narrow, specific set of hardy, acid-tolerant survivors was making it through to the intestine intact. That narrowing is the real answer buried inside the acidity finding, and it points to something researchers describe as a survival bottleneck rather than a simple sterilizing bath. The vulture's stomach does not merely dilute the bacterial load coming in from a rotting carcass. It performs an aggressive act of biological selection, killing off the overwhelming majority of what enters, and allowing only a specific, narrow community of bacteria, ones the vulture's own gut has apparently evolved a working tolerance for, to survive the passage and establish themselves further down the digestive tract. The vulture is not simply immune to what it eats. It has, over evolutionary time, built a filtering system precise enough to let a select handful of microbial passengers through the gate, while destroying almost everything else trying to follow them in. That still left the bald head itself only partly explained, because a bird capable of neutralizing nearly everything it swallows still has to survive direct, repeated skin contact with that same bacterial load every single time it feeds. And skin infections do not require ingestion to take hold. Watch the vulture again as it withdraws its head from the zebra's body cavity, feathers absent from the neck and skull entirely, exposing bare, wrinkled, mottled skin that would, on almost any other bird, be covered and insulated. Ornithologists have long proposed that this baldness serves feeding hygiene directly. A fully feathered head plunged repeatedly into a carcass would trap blood, fat, and bacterial residue against the skin in a dense mat of soaked plumage, an environment ideal for infection to take hold and nearly impossible for the bird to fully clean. Bare skin, by contrast, dries quickly, sheds residue easily, and is regularly exposed to direct equatorial sunlight strong enough to carry meaningful ultraviolet sterilizing effect across the course of a single day spent largely outdoors. There is a second use for that same bare skin, and it surfaces not at a carcass, but in the open heat of the plain itself, in a behavior that looks, at first glance, deeply unappealing and turns out to be a second layer of the same defensive architecture. Vultures of multiple species, including both Old World gyps vultures and New World species like the turkey vulture, engage in a behavior ornithologists call urohydrosis. They defecate directly onto their own legs, coating the exposed skin in a thin wash of liquid, urate-rich waste. Documented first in detailed anatomical terms by researcher Donald Hatch in a 1970 study of New World vultures. The primary confirmed function of this behavior is thermoregulatory, evaporative cooling that draws heat away from the legs, the same way sweat cools a mammal's skin, an essential mechanism for a bird spending hours standing in direct tropical or desert sun. Some researchers have additionally proposed the waste itself may carry a secondary antibacterial benefit given its chemical composition, though that particular secondary claim remains less thoroughly confirmed than the cooling function itself, and any honest account of this behavior should present the two functions with that difference in certainty intact. That still does not explain how these two very different vulture lineages
separated by an entire ocean and tens of millions of years of independent evolution, arrived at such similar solutions to the same problem, and the fuller answer requires stepping back from any single bird and looking at how differently the Old World and New World vultures actually find their food in the first place. This is where a pattern interrupt is worth taking, because the story shifts here from the gut to the skull, and specifically to the brain sitting inside it. Old World vultures, the species soaring over the Masai Mara right now, locate carrion almost entirely by sight, circling at enormous heights and watching not just the ground but each other. A single bird's sudden dive toward a carcass acting as a visible signal that draws in dozens more from kilometers away. New World vultures, including the turkey vulture found across the Americas, do something almost no other bird on the planet does. Many species use smell. A landmark 1964 study by researcher Kenneth Stager, working with turkey vultures at the Los Angeles County Museum, released concealed ethyl mercaptan gas, the same sulfur compound responsible for the smell of early decomposition, into the open air and documented turkey vultures locating and descending on the invisible source directly, guided by an enlarged olfactory bulb structure in the brain that is unusually developed for a bird, a sensory pathway most other avian species rely on only minimally, if at all. Two completely different sensory systems, sight in one lineage, smell in the other, converging on precisely the same outcome, locating a decomposing carcass as early as possible after death, before bacterial populations inside it have had time to multiply into the truly dangerous concentrations that build over the following days. Speed itself, it turns out, is not incidental to the vulture's survival strategy. It is a defense in its own right, working alongside the acid gut and the bald head, rather than separately from them. A carcass found and stripped within hours carries a meaningfully lower pathogen load than one left to sit for 2 or 3 days in the heat, and both sensory strategies, sight-based social soaring and smell-based solo tracking, function as the earliest possible layer of a defense system that continues all the way down through the throat and into that acid stomach. There is a stakes moment buried inside that speed, and it widens this story well past the individual bird circling over a single zebra carcass on the Mara. A carcass that sits undiscovered and unconsumed, does not simply decompose quietly in place.
It becomes an active source of pathogen amplification and spread, a breeding ground where bacterial populations multiply, where flies lay eggs and disperse further, and where other, less resistant scavengers, feral dogs among them, risk direct exposure to concentrations of bacteria and toxins that a vulture's gut was built across millions of years to specifically survive, and theirs was not. A landscape with a healthy, active vulture population functions, in the most literal sense, as a sanitation system, carcasses located and reduced to bone within hours rather than days. Pathogen loads contained inside the one animal on the food chain, evolutionarily engineered to absorb them safely, rather than left to circulate outward into the wider ecosystem. That sanitation role is not a passive benefit humans get to enjoy from a distance. It has been tested, catastrophically, in the real world, and the results reframe the entire question the script opened with, because the same vultures that can shrug off anthrax, botulism, and cholera in their food turned out to have a vulnerability nobody had anticipated, one with nothing to do with bacteria at all. Beginning in the 1990s across India, Pakistan, and Nepal, populations of gyps, vultures, the same genus as the white-backed vulture feeding on that Mara carcass, began collapsing at a rate researchers initially struggled to believe. Field surveys led by conservation biologist Vibhu Prakash, tracking population numbers across India through the early 2000s, documented declines exceeding 95% for multiple gyp species within roughly a decade, a crash so severe and so fast that it ranks among the steepest population collapses ever recorded for any bird species anywhere on Earth. The cause, identified in a 2004 study led by Lindsay Oakes and published in Nature, traced back not to any pathogen at all, but to a veterinary anti-inflammatory drug called diclofenac, widely administered to sick or aging cattle across the region. Vultures, feeding on the carcasses of cattle treated with the drug, shortly before death, ingested residual diclofenac along with the meat, and the drug, harmless to the cattle it was intended for, triggered catastrophic kidney failure in the vultures that consumed it, a toxic vulnerability. Their famously resilient digestive systems had no defense against whatsoever, because it was never bacteria they needed defending against in the first place. The consequences of that collapse rippled directly into human health in ways researchers had not fully anticipated going in. With the region's primary rapid response carcass consumers largely gone, cattle carcasses across India began sitting far longer before being disposed of by any other means, and feral dog populations, no longer competing with vultures for that food source, expanded rapidly to fill the gap. A 2008 economic and public health analysis led by Anil Markandia, examining the downstream effects of the vulture collapse, connected that surge in feral dog populations to a documented rise in dog bites and, following directly from that, an increase in human rabies exposure across affected regions, a disease vastly more lethal to humans than nearly anything a vulture itself was ever at risk of catching, from the carcasses it used to consume so efficiently. The lesson embedded in that collapse is not a small one, and it belongs at the center of this story rather than at its margins. An animal engineered by tens of millions of years of evolution to absorb, neutralize, and contain some of the most dangerous bacterial pathogens on the planet, safely, silently, every single day, turned out to be entirely undefended against a threat evolution had never given it any reason to prepare for. A synthetic compound, introduced by humans, moving through the exact same food chain the vulture had spent its entire evolutionary history mastering, the very efficiency that made this bird, nearly untouchable to Clostridium and Salmonella, made it just as efficient at concentrating a toxin. Nobody built it to survive. Back on the Maasai Mara, the white-backed vulture lifts its head from the zebra's emptied ribcage, throat and neck slick with fluid dense enough in bacteria to have killed almost any other animal on this plain within the week. It shakes once, flings a scrap of tissue aside for a subordinate bird waiting at the edge of the crowd, and steps back from the carcass, wings half spread, already angling itself back toward the thermal that will carry it 1,000 meters up into clear equatorial air. It carries inside it, right now, the accumulated result of tens of millions of years, spent solving a problem that would kill almost anything else that tried to solve it the same way. An acid gut, precise enough to filter friend from foe among an army of bacteria. A bald head built to shed what the gut does not destroy. A nose, or a set of eyes, built to reach the carcass before decay outpaces even that defense. It is, in the most literal biological sense, one of the most disease-resistant large animals on the planet, and it remains, even now, entirely defenseless against the one threat its own evolution never saw coming: